We can start.
Yeah, okay. So,
Welcome again to the European and Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Professor Raschid Abedin from the University of Hamburg. The title of his talk is Classification of D-bialgebra structures via algebraic geometry. Please, Rashid.
yeah, thanks a lot for the introduction, and thanks a lot for the opportunity to talk about my research. So, this talk will be split into essentially two parts. First, I will talk about Lie bialgebra structures and the particular class of Lie bialgebra structures on formal power series algebras, their relation to algebraic geometry, and the classification of these structures. And then I will talk about non-associative algebra generalization of these kind of structures and apply similar methods to also explain classification results which can be achieved in this more general setting. So first about Lie bialgebra structures. The motivation for the study of Lie bialgebra structures essentially comes from the study of quantum integrability, which was related to the theory of quantum groups in the 80s. And through the relation of both objects with a so-called Yang-Baxter equation. These quantum groups admit a classical limit. They actually quantize specific Poisson structures on Lie groups. And these Poisson structures, by passing to the Lie algebra level, are precisely correspondent to Lie algebras with an additional structure. And these are precisely Lie bialgebras, one of the central objects of my talk. And similar to the relation of quantum groups with quantum integrability, Lie bialgebras are very important in the theory of classical integrability through the relation to the classical Yang-Baxter equation. So I want to, as a motivation, I want to explain this relation a bit more. So recall that for a classical mechanical system, so we have some Poisson manifold and a Hamiltonian on it. The goal is always to solve the equations of motion. And in the theory of integrability, one of the important methods to actually prove integrability of such a classical mechanical system, which essentially means that the equations of motions are exactly solvable, is to represent the equations of motions in terms of Lex representation. In particular, we find functions on our phase space, which now take value in some Lie algebra, such that this differential equation on this side, in terms of this Lex representations, gives us actually equivalent informations as the equations of motion. And the advantage of finding such a Lex representation is that essentially it provides already a lot of constants of motion from invariant polynomials on this Lie algebra L. For example, if we have some embedding into matrices, one could look at just a trace of powers of matrices and can see that like this Lex representation here implies that these already give us constants of motion. So now for integrability, it's actually very important to see, are these constants of motions Poisson commuting among each other? And this is where actually our central object will come into play. It turns out that this involutivity property can be expressed in terms of an additional constant of the system, the so-called R matrix, if the Poisson bracket of the Lex matrices can be expressed by Lie brackets with this R matrix. And then if additionally these constants of motions are independent, one really has the desired integrability of the system, which again means there are some very strong methods to actually exactly solve the equations of motion of the system. So now this equation here actually gives the fact that we are looking at a Poisson bracket actually gives constraints of the possibilities of how these R giving the Poisson bracket in such a form can look like. And if we assume that this R matrix does not depend on our phase space variables, so it's constant, and if we assume that it's skew-symmetrics, two things which actually occur a lot in applications, then a sufficient condition for this Jacobi identity is precisely the classical Yang-Baxter equation. Now, what is the relation of this structure to Lie algebras? Well, it turns out that the co-boundary to a solution of this classical Yang-Baxter equation actually equips a Lie algebra with an additional structure, such namely a so-called Lie co-bracket, a map going from L to the tensor product, which provides by dualizing a Lie bracket on the dual space of the Lie algebra. And now the Lie algebra and this dual Lie algebra structure, they are compatible by the fact that if we start with such a co-boundary, it would satisfy such a co-cycle condition. And so in general, having these two properties, even like for a more general co-bracket than these delta R, these are by definition Lie algebras. Now, in general, we have a correspondence between Lie groups and Lie algebras. And so as I mentioned already in the diagram in the beginning, it turns out that these Lie algebra structures are precisely infinitesimal analogs of Poisson brackets on the Lie group associated to a Lie algebra, which has an additional compatibility with the group structure of this Lie groups. And these Poisson structures with a compatibility, they are called Poisson Lie groups, these groups. So now, actually, our setting is slightly different. Namely, before I come to my setting, one important additional information a Lie algebra automatically provides is that if we look at any such linear map from L to L tensor L, we can actually equip L star with a multiplication. At first, without giving any assumptions to delta, this multiplications does not have any kind of particular properties, but we can always consider this expression as a multiplication for elements in the dual algebra. And it turns out that we can then equip the direct sum of the Lie algebra with its dual also with a canonical multiplication such that both the space and the dual space are subalgebras, and the pairing coming from evaluating elements of the dual space on elements of L is assumed to be invariant under this multiplication, or in terms of general algebras, associative. And this abstract, kind of confusing no assumptions on delta language was chosen by me because the consequence is that actually the property of this delta to be a Lie bialgebra is now equivalent to the fact that this object constructed in this way is a Lie algebra. So if this is a Lie algebra, obviously the dual space will be, as a subalgebra of a Lie algebra, is automatically also a Lie algebra. And it turns out that this invariance condition implies the co-cycle condition desired by delta. And this Lie algebra will be very important for us, and it's called the classical double of a Lie bialgebra L delta. So now, actually, our setting will be slightly different than just the setting mentioned above. because actually coming from applications in the theory of integrability, in many cases, the Lex matrix is actually dependent on an additional so-called spectral parameter. And in this case, the R matrix is dependent on two, on this spectral parameter twice. And this kind of corresponds intuitively to the fact that the Lie algebra we look at is actually the Lie algebra of formal power series in the spectral parameter, where in many important cases, this Lie algebra will be some finite dimensional simple Lie algebra over the complex numbers. And I like to mention now here that actually a lot of the story I will tell now in the rest of this talk can be generalized to other fields of characteristic zero, but for simplicity of presentation, I will remain over the complex numbers throughout the whole talk. And a specifically important example of such an R matrix with spectral parameter is the so-called Young's R matrix. It's given by a very simple formula. It's just the quadratic Casimir element of our simple Lie algebra divided by Z1 minus Z2. And it turns out that this will satisfy the classical Yang-Baxter equation adjusted to the spectral parameter case. And it controls kind of well-known interesting integrable systems, which are known as classical Godin models. Now, why am I saying that although I'm writing everything like kind of it fits into the setting before, the difference here in this setting is that actually the co-bracket associated to an R matrix of this form in general takes values in formal power series in two variables. And this space is larger than the tensor product of two formal power series. So essentially we have to take a completed tensor product instead of just a tensor product. And this kind of notion brings us to the notion of a topological Lie-bialgebra structure, which is just the intuitive adjustment of a Lie-bialgebra in this setting to topological notions. So we have the topologically completed tensor product instead of tensor product, and we actually induce a bracket on the continuous dual instead of the complete linear dual. Now, the notion of double also just is adjusted very naturally to the setting, and the goal of the first part of this talk will be to understand actually the classification of these kind of Lie-bialgebra structures on our formal power series Lie algebra. And kind of the starting point of the study we will give here is actually the classification of topological doubles of these kind of Lie-bialgebra structures given by Montaner, Stolin, and Zilmanov. Namely, it turns out that actually for these topological Lie-bialgebra structures, the topological double is either isomorphic to the double associated to the trivial Lie co-bracket, so just taking the zero map, which can also be described explicitly, but I will skip it here since I don't really consider this case, or it has some other kind of interesting doubles, namely the double will look like the sum of G-valued Laurent power series with some second component of truncated polynomials. However, they're not arbitrary truncated polynomials. They're either, we have here really just zero. So if we truncate immediately by zero, so we only have Laurent power series, or we truncate at degree degree 1 or 2. So hereby we should mention that the formal power series, which should always live inside the double, are actually here embedded by the diagonal embeddings. So here in our Laurent power series, we already have the formal power series living inside. And in the second component, we just truncate the same element we plug inside the first component. So a remark about how this result is actually achieved. Actually, the proof of this result splits into two parts. First one shows that we have this general form for arbitrary high n, and then actually further, still very complicated analysis actually shows that after two, none of these n actually arise as a topological double of a Lie algebra structure. So this kind of proof splits into two cases. From this explicit form of the topological double, one can actually see that these Lie algebra structures, delta, they always come from solutions of the classical Yang-Baxter equation of a particular form. Namely, these are skew-symmetric series in two variables, which are regular except for a diagonal, having a diagonal pole with Casimir and some coefficient of the Casimir coming from the particular double 0, 1, or 2. And air matrices of this form I will call non-degenerate, while if we don't have such a diagonal pole, these series would be referred to, or solutions of this classical Yang-Baxter equation would be referred to as degenerate. So if we now consider particularly non-degenerate bialgebra structures, this classification problem is actually equivalent to the classification problems for solutions of the classical Yang-Baxter equation. And it turns out that actually here these D-bialgebra structures which have a trivial topological double are kind of wild. So from now on, I will only talk about these non-degenerate bialgebra structures. So, and the way I actually want to study these kind of structures is by using an algebro-geometric approach to the classical Yang-Baxter equation, which goes back to Cherednik, developed in the 80s, and then it was further developed in a fairly general setting by Boban and Gallinat. Which essentially gives a recipe of how one can associate to a particular set of algebro-geometric datum a solution of the classical Yang-Baxter equation. The algebro-geometric datum in place here is a pair of an irreducible cubic plane curve and a sheaf of Lie algebras on this curve, where if you're not so comfortable with sheaves, you can think of a vector bundle over this curve having a Lie algebra structure on its sections. And this is kind of an important generalization of vector bundles over this curve, which have the particular property that they don't admit any kind of cohomology. So the zeroth and first cohomology group of this sheaf vanishes. And it has an additional property, namely, it should have at least one fiber isomorphic to our starting simple Lie algebra G. And it turns out that for every such cohomology-free sheaf, one can actually define a killing form for this sheaf of Lie algebras analog to the killing form of a Lie algebra. However, in general, this killing form would only take values in the normalization of the curve in place. So we have to de-singularize this possibly singular curve to actually define a killing form. And an additional assumption to get such a geometric datum here is that this killing form is really defined over the possibly singular curve as well, not only in the normalization. So, and if one has such a geometric datum, one can show that this datum, from this datum, one can construct a canonical section. It's essentially having this kind of killing form gives you something like a geometric analog of the Casimir element, and one takes the unique section having a diagonal residue with having the Casimir element as diagonal residue. This element will solve the classical Yang-Baxter equation. So at first, this sounds actually like a kind of complicated abstract thing, but essentially why it's important to me is that this geometric datum is actually very rigid and fairly beautiful if one feels comfortable with these words. And the idea of classification is that if we could associate two solutions of the classical Yang-Baxter equation through some geometrization method, geometric CYBE data, then this will actually give a classification through geometric language. And to actually explain how this geometrization can be built, for simplicity, let us assume that we're in this double associated to n equals to 0. Then our double is essentially just a formal Laurent power series. And Lie bialgebra co-brackets are uniquely determined by a subalgebra in this double, namely the subalgebra representing the topological dual. And this subalgebra is by definition through the evaluation pairing on the classical double Lagrangian with respect to the pairing on the space, and complementary to the original Lie algebra, since this is how the double is built, right? It's the Lie algebra direct sum with its dual. And it turns out that these kind of Lie algebras, which are almost, or in general, almost complementary to a formal power series, they have been studied by Ostapenko, who proved the following interesting theorem, which actually holds for any simple non-associative algebra. Namely, if one starts with a Lie subalgebra in our formal Laurent power series with values in this simple non-associative algebra, which intersects from a power series only finite dimensionally, and the complement of formal power series with this algebra is only finite dimensional. So in particular, this is our setting is stronger, so this is a more general setting. Then the multipliers of the subalgebra are actually very large. So in general, these multipliers for general subspaces, they can simply be only complex numbers. But through these conditions, it's possible to show that actually starting from a certain order of pole, Laurent power series with this order of pole and having this multiplier property will exist. And why is this important? Well, actually, this gives the possibility to geometrize these kind of subalgebras in a very uniform way. Namely, the idea is one can take the affine datum. We can think of this of any subalgebra of the multipliers of finite codimension now as regular functions on some affine curve, and we can think of this Lie algebra W, which is stable under multiplication of O, as a kind of sheaf on this affine curve, and then using a projectification method, we can actually get some projective algebro-geometric datum from this affine datum. Pictorially, the affine curve having regular functions O is just some affine curve, and on it we have this W, and we think of it as a coherent sheaf on this affine curve. And what we do is we add a smooth point at infinity, and at the smooth point, we essentially think of formal power series of G with values in G as kind of functions on the neighborhood, on an infinitesimally small neighborhood of P. And we glue these two geometric datum together to get a projective datum. So now this is a very general method coming immediately from the work, essentially by projectifying the work of Ostapenko. And in our stronger setting, it turns out that these multipliers, they're not just very large in the abstract sense that the codimension, if added with all formal power series, is finite dimensional. One can even show that this dimension has a lower bound. Namely, one can always find a subalgebra such that the codimension is 2. This uses in a very essential way this Lagrangian property. However, the consequence is that if one goes through this projectification, one really gets a geometric CYBE datum. And the important part of this codimension property is that if you think back to the definition of the geometric classical Yang-Baxter equation datum, the curve was assumed to be an irreducible cubic plane curve, and this is why this is actually essential. This actually gives you the fact that it's a cubic. And together in a work with Stepan Maximov, Alexander Stolin, and Efim Zilmanov, we actually adjusted this arguments for the case n equals to 0 to the case n larger to 0 to get a uniform geometrization method from this Lagrangian splittings of our doubles to geometric classical Yang-Baxter data. So why is this now helpful for classification? Well, in the geometric classical Yang-Baxter datum, the underlying curve is a cubic plane curve. And these are actually fairly simple, and they actually fall into 3 different categories. These categories depend on the discriminant of this cubics. First, if the discriminant is non-vanishing, then the curve is smooth, and smooth cubic plane curves are elliptic curves. So pictorially, one gets a torus. If the discriminant vanishes, but these coefficients do not, then X has a unique nodal singularity. So pictorially, one takes one circle on the torus and squishes it to a point. And finally, if both coefficients are 0, one actually gets a unique cuspidal singularity, which is essentially like a sphere having one cusp. And so these 3 types. So let us go back to a simpler situation where n is equals to 0, where essentially we're studying again Lagrangian decompositions of G-valued formal Laurent series. And recall that these are not in bijection with solutions of the classic Yang-Baxter equation having this diagonal residue but no additional coefficient here. Then these 3 classes of curves give restrictions to the class of solution of the classical Yang-Baxter equation. One can prove that then R up to appropriate equivalence relations, which are very natural coming from the setting. If the curve is elliptic, then this R will be an elliptic function in both variables. If the curve is a nodal, it turns out that this R will be a rational function of exponentials. And if it's cuspidal, it will be simply a rational function. And one refers to these solutions then as elliptic, trigonometric, and rational, respectively. And this actually reproduces geometrically a very classical result by Belavin and Drinfeld from the 80s, who, using very complex analytic methods, actually gave the similar classification for analytic solutions of the classical Yang-Baxter equation, which depend on the difference of their variables. Now, for the cases n equals to 1 and n equals to 2, which we have then studied late in the follow-up work, it turns out that one does not have all three curves appearing, but for example, in the case n equals to 1, the only curves which appear are the nodal curves. And in this case, one gets one gets that R is automatically in the class of so-called quasi-trigonometric solutions. These are solutions of the following form. And for n equals to 2, one can show that the only curves which can appear are actually cuspidal. And in this case, one gets to the class that R is automatically of the class of so-called quasi-rational solutions. So in total, using this geometric method, one gets a complete classification of topological D-bialgebra structures in the sense that all of them are given by a R matrix. This R matrix is either degenerate, so it does not have this diagonal pole. This was correspondent to the fact that we have double which is isomorphic to the double of the trivial co-bracket, or it falls into the three cases coming from n equals to 0, so it's elliptic, trigonometric, or rational. So these cases, these classes which were already considered by Belavin and Drinfeld, or it falls into the n equals to 1 and n equals to 2 cases, so that they are quasi-trigonometric or quasi-rational. And actually, in all of these non-degenerate cases, more fine classifications of these classes already exists in literature. Namely, Belavin and Drinfeld, in the same work mentioned before, already classified elliptic air matrices and trigonometric air matrices. And then later, Popp and Stolin classified quasi-trigonometric air matrices using a particular class of datum as Belavin-Drinfeld used for the classification of trigonometric solutions before. And then Stolin in a later work with a co-author classified quasi-rational solutions also in terms of a fairly particular set of parameters. So essentially, the fact that one has really this complete categorization gives a complete, more detailed classification through earlier results, since all of these classes were already known. Now, I want to pass to the second part, namely actually this very central theorem by Ostapenko for this geometrization method was already mentioned to actually work for more general simple non-associative algebras. And so in a follow-up work, I considered more general non-associative bialgebra structures, but however, in a general non-associative setting, there is actually not just one, depending on which classes of algebras you look at, there's not just one natural way to define what even a bialgebra structure means. And it turns out that, like, as you can imagine from the arguments before, and from how essential the role of the classical double was, that actually the way how we should generalize bialgebra structures in the sense that we want we would need for these geometric methods to work would be to define a bialgebra through the property that it has a classical double in the same class. And these kind of bialgebras, they were first defined by Belavin in end of the 90s, and they were referred to as D-bialgebras by him. And essentially, they're defined as follows. As before, for every algebra, which is here we don't impose any kind of axioms at first, so just some general algebra, a non-associative algebra, having some co-multiplication, again, without any axioms for now, one can define multiplication on this direct sum of the space and its dual space using the same properties as before. So assuming that both spaces should be subalgebras, such that multiplications on elements of A and elements of in the dual space of A are already defined here. And then imposing the condition that this evaluation pairing should be associative, which gives us a unique way to write down actually mixed multiplications of elements of A and elements of A dual. And now such an algebra with a co-multiplication is called a D-bialgebra in a particular class of algebras. For example, we have until now considered Lie algebras, but we could have now considered associative algebras or Jordan algebras or even more general other classes of algebras. Then it's a D-algebra in this class if its classical double is of the same class. So what we have seen until now is essentially, as I mentioned on the slide about classical double, this definition identifies Lie D-bialgebras with Lie bialgebras. Since Lie bialgebras are precisely defined by the fact that if we have a co-bracket and or not defined, but it's equivalent that if we have a co-bracket and the classical double is the Lie algebra, then these Lie bialgebra axioms are satisfied. So what happens for other classes of algebras? And here we will actually see that, for example, in the case of associative algebras, we do not get the usual notion of associative bialgebras maybe more people are aware of. What one gets instead is actually up to order of multiplication, what is known as balanced infinitesimal bialgebras introduced by Aguiar. And essentially these appear they have applications in combinatorics, and they appeared also in the study of compatible multiplications. And the case of Jordan D-bialgebras, which are then simply called Jordan bialgebras for the lack of different natural bialgebra structure on Jordan algebras, introduced by Belavin, was studied by him in several follow-up works, and they are actually quite interesting due to relations to associative and Lie D-bialgebras in a similar way as Jordan algebras are related to associative and Lie algebras. Moreover, they are related to symplectic forms of Jordan algebras, and actually something we will see occurring for D-bialgebras in general is that actually one gets kind of further generalizations to of the classical Yang-Baxter equation to other kinds of algebras. Now, in our setting, we actually only want to look at now simple non-associative algebra with the additional property that it admits a non-zero associative bilinear form. So, for example, in our Lie algebra case, this is multiples of the Killing form. But in the associative and Jordan case, one can define similar trace forms to satisfy such an axiom. And now we want to pass to the formal power series case again. So what we actually want to study are topological D-bialgebra structures on the formal power series with coefficients in such a simple algebra. And in our case, we assume that their double already has the form of this non-degenerate doubles as in the Lie algebra case. So why we do this assumption actually in cases I looked so far, this is actually, apart from the degenerate case, still the only case which one would expect from this kind of axiomatics. But for general non-associative algebras, I have no mechanism to actually prove such a statement. And since this is a very essential form for the geometric analysis, here this will be an assumption, and I will call these D-bialgebra structures precisely non-degenerate. However, I do not assume a bound of this natural number. So it's like in the first step of the classification of doubles, but second step is still something I will consider in the analysis. And due to this form of the classical double, one can actually generalize this statement about how the form of this co-bracket, namely, it turns out that the co-bracket is again given by some structure constant R, and this R has again this particular form, which we call non-degenerate form again. So again, it's just formal power series in two variables with this diagonal pole with residue Casimir times some formal variable. And this element has to satisfy some adjustment of the classical Yang-Baxter equation, which, for lack of better terms, I called a classical Yang-Baxter equation to remember in what kind of algebra these multiplications here take place. Here, this element, which replaces the Casimir element, is precisely the dual of this bilinear form. So as soon as we have this bilinear form, we can construct such an analog of the Casimir element for our algebra. So now we have already mentioned that Ostapenko's theorem actually applies to this very general setting, and we also have actually no issue with projectification. So essentially, from this general setting and the assumption that we are looking at these non-degenerate topological bilinear forms, we still have a general geometrization method at hand by just using the same arguments as in the Lie case, and we get some geometric datum. However, at this stage, this geometric datum has not at all this rigidity as in the Lie algebra case, where we really have this geometric classical Yang-Baxter datum, where, for example, this X is a cubic curve. And in general, there, at least as far as I have seen, there I had to make a specific, very weak assumption on this pair of simple algebra with bilinear form to kind of get a first step of geometric results. And I call this kind of restriction geometrically admissible. And essentially, this geometrically admissible condition is constructed precisely to, as in the Lie case, get actually an extension of the bilinear form to the geometric setting in the sense that we have some pairing with values in the regular functions on the normalization. So, for example, in the Lie case, this was always the case. This is automatic for Lie algebras. And this existence of like a geometric extension of this bilinear form beta actually implies, by using Riemann-Roch theorem, that the normalization has genus of at most one. And actually, why this is already interesting is that what I could see from this analysis is that this restriction on the genus of the normalization actually bounds the possibility of n here. So in a sense, in the Lie case, even this geometry can be used to give a new proof of this bound on n theorem from the paper of Montaner, Stolin, and Zilmanov. It extends to all algebras, so including Lie algebras, which have this geometrically admissible property. And just a note about this geometrically admissible, actually, I was not even able to see any kind of example for simple non-associative algebras which do not satisfy this property, since actually every time this bilinear form can be expressed in terms of the structure constants of A, this geometric admissibility is already satisfied. So for associative and Jordan algebras, similar to Lie algebras, since we can write down this bilinear form using traces essentially, we have this admissibility. So for associative and Jordan algebras, this non-degeneracy is actually again restricted to n equals to 1 and 2, 0, 1, and 2. So now, what does one have to do to get really a same rigid classification as for the classical Yang-Baxter equation? Turns out that this kind of geometrically admissible does not satisfy. One has to refine it a bit more. But if you refine it a bit more in a way I will give only an intuition again in the following, turns out that with a slight refinement, one can again see that this geometrization can be adjusted to a very natural analog of a geometric classical Yang-Baxter datum to this setting of a non-associative algebra, where in particular the curve is again an irreducible plane cubic curve, where recall that this was really kind of the ingredient where one already saw that one has to have some kind of very rigid categorification of solutions. And essentially the intuition behind this strong geometric admissibility is that our algebras we look at, they should have some kind of theory of rigidity where the existence of a non-degenerate associative bilinear form implies rigidity of the algebra, where essentially rigidity means that if we have like a variety of algebras, for example, Lie algebras, where variety means that we can think of a general class of Lie algebras as just given by structure constants, and these constants satisfy this quadratic polynomial constraint given by Jacobi identity. And for example, for Lie algebras, semi-simple Lie algebras are automatically rigid. And if you have a non-degenerate killing form, your Lie algebra is semi-simple and therefore rigid. And something similar you can do for associative and Jordan algebras. So again, these like largest classes of algebras you would have in mind satisfy this additional condition one needs for like a more detailed analysis here. And consequence is similar to the Lie case. If we now start with a strongly geometric admissible algebra, then here it's a typo. For every non-degenerate bialgebra structure, one can see that either the associated curve X is elliptic. So interesting note here, in the general case, I could not prove that the R matrices in this case are elliptic functions. So this was something which kind of really used Lie theoretic notions in a sense. But the curve is either elliptic or the co-bracket is given by an R matrix, which is really trigonometric, rational, quasi-trigonometric, or quasi-rational, which these parts of the argument are as in the D-bialgebra case. However, about this weird occurrence of the elliptic case, it turns actually out that for other classes of algebras other than Lie, for example, in the associative and Jordan case, where one has a unit, the curve is automatically never elliptic. So actually, in these like big other classes of algebras, I could not even check what happens in the elliptic case because elliptic case cannot occur. So let us actually specify now this classification for another class of algebras than Lie, namely for an associative algebra, in which case we have algebraically closed field characteristic 0. So we essentially look at matrices, and the bilinear form is essentially given by the trace. Then it turns out that this classification is pretty large, namely it turns out that as in the Lie case, every topological Lie bialgebra is either degenerate or, here it's a typo again, I mean non-degenerate. I called this admissible in an earlier version of this story. So again, we made this assumption on the topological double that it is of this non-degenerate form for everything we study. But as for Lie algebras, actually in the associative case, the only other case is this degenerate case where the topological double is isomorphic to the topological double of the trivial co-bracket. Furthermore, it turns out that actually this trigonometric and quasi-trigonometric solutions of the classical Yang-Baxter do not exist in the associative case. So what we end up with is that the only structures which exist are the quasi-rational ones. So sorry, I don't even know how this ended up here. And these quasi-rational structures, they can be classified in a similar vein as quasi-rational structures for Lie algebras were classified by Storlin. So essentially, in the case of associative algebras, this geometric classification can really be made a lot more specific, and it really gives a very clear classification for associative topological D-bialgebra structures. Now, what I noticed during the study of the non-existence of trigonometric and quasi-trigonometric structures is that essentially, again, the constraint comes from the existence of a unit. And although I'm not really able to prove it now, I have the feeling that for unital algebras, as for the absence of elliptic curves, there potentially also do not really exist nodal curves. So one really ends up with essentially like quasi and rational and quasi-rational solutions. And an immediate outlook, which I have not or really had the time to study in like a lot of detail, would be to look actually at a similar kind of specification as was done here to the associative case for the Jordan case, where I actually, again, kind of expect that one has essentially only degenerate and non-degenerate in the previous sense bialgebra structures, and no trigonometric and quasi-trigonometric structures, but I still don't really know. Yeah, thanks a lot for your attention.
Thank you very much for your interesting talk. Are there any questions? There is a question in the chat.
Oh, wait. I have to open it.
Can you read it or?
I don't see it right now. I think maybe, where can I see the chat? There it is. Okay. Could you give an example of solutions of the CYBE, if possible? You mean now for a more general class of algebras, or because I have given, for example, Yang-Baxter metrics? This is actually something you can also write down for other classes of algebras always. So there is always the analog of Yang-Baxter metrics. Other than that, I think I don't really have the possibility to write something down, but there are actually fairly easy quasi-trigonometric solutions of the Yang-Baxter equation, for example. If we look at, I will answer the second question as soon as possible. If we look at here the general form of quasi-trigonometric metrics, what you can do is, for example, as a polynomial, take the constant tensor given by essentially the positive nilpotent part of your Casimir element and half of the Cartan part of the Casimir element, and one gets the solution of the classical Yang-Baxter equation as well. I hope this gives an example as you want. Where is the topology in topological Lie algebra? Well, the idea is that actually the notion, how this notion of Lie algebra is adjusted to form a power series, is that one actually puts on the set of formal G-valued form a power series with coefficients in G, the Z-adic topology. And then with respect to the Z-adic topology, for example, this is really the set, the space of continuous functionals. And this is really a completion of the tensor product with respect to these Z-adic kind of topologies. So this is where this name topology actually stems from. One could really, and we have set up some kind of language for this with Maximov, Stolin, and Zilmanov about more general topological Lie algebras and how you would adjust this notion of bialgebra in a similar way. But here, Z-adic topology is actually kind of so natural that you don't really feel the topological note.
Okay. Other questions? Comments? Or remarks? If no, let's thank Raschid again. And okay, we will resume on next Monday.
Thanks a lot for your attention, and bye.
Thank you again. Bye-bye.